Hi, I'm Mr. Franklin, and up until this point, we've really just been looking at numbers and conversions of pressure and temperature, and we haven't necessarily been exploring what some of that means. So I thought it best that I'm going to take a step back here, and I'm going to go back and I'm going to explain a couple things, okay? So let's start with our ideal gas law. So I have a gas. Now, moles is really a representation of how much of a gas I have. So let's say I have a container, maybe a tank of some kind that contains gas. And let's just say, for this purposes, let's just say that we've got some methane in here. We've got methane gas, and it's bouncing around in here. Now, moles is based on the mass of it, right? But we learned from our triangle that if I have 1 mole of gas, I can actually figure out how many particles, using Avogadro's number, are in this container, okay? So if I have a number of moles in here and they're bouncing around, I can actually determine how fast are they moving in here, and that's where we look at the temperature in Kelvin. So if it's a low temperature, they're not moving very much, and if it's a high temperature, they're moving a lot, okay? Now, as these particles are bouncing around in here, they're going to collide or run into the walls of the container. As they do that, they're going to hit the walls of the container, and without going into a lot of detail on exactly how forces are defined in physics, because it's rate of change of momentum is the technical definition, okay? So, but that involves collision, okay? So this particle collides with the surface, basically applies a force to the surface over the area of the wall. So if we could like take a balloon or this tank and cut it and lay it out, and we could measure the area inside that tank, we could take our force divided by area and we could get our pressure. So our moles and our temperature times this constant can actually tell us what that pressure might be. Well, if you think of pressure as something that's pushing against something, especially like a balloon. If I blow up a balloon, what happens is you put more air in there. It starts to expand, right? You increase the volume. Okay? So, if this was a metal tank, can you increase the volume? No. So the volume will stay constant, but the pressure can continually increase as you add more stuff to it, okay? So that's kind of a basic rundown of this. Now what we're going to do is I'm going to go back and kind of show this in another way using some math, because really what we're going to get into and what we're interested in and why all of this stuff is important is what happens in a chemical reaction. In a chemical reaction, I might have sodium, which is a solid, plus chlorine, which is a gas, produce a solid. Okay? Well, if this gas is in a tank and then I start to mix it together, or maybe I have something that, like we did the other day where we had NaHCO3 and it produced CO2 bubbles, gas. You can actually do this. You can take baking soda, put a balloon over if you can get the balloon over the cup, put the baking soda in, pour some vinegar in, and you close it over the top with the balloon's going to inflate because suddenly you're producing a gas. Okay? So why is this important? We're looking at how gases change. Okay? So to look at how gases change, we're going to take our equation and we're going to turn it around in a way that we can talk about change. So to do this though, the baseline of this is we have to look at what will never change. So which number never changes, no matter how you look at this? this one, right? It's a constant. So you could do this. You could divide by n on both sides, and you could divide by t on both sides. So n divided by n cancels to 1. T divided by t cancels to 1. And now I've got PV over n times t equals R. Now, let's say that, just for grins, that all of these values equal 1. So 1 times 1 divided by 1 times 1, which would mean R is equal to 1. Now, this is pretending like we're using different units from our normal R, because we know R equals 0.0821, right? I'm using 1 to make the math easy, right? 1 times 1 is 1. 1 times 1 is 1. 1 divided by 1 is 1, right? Okay. Easy math, right? Okay, so, but now we're going to change something. Okay? I'm going to change, let's say we change the number of moles. I'm going to put more baking soda in because I want to see more stuff happen. So I'm going to change that to a 2. I'm going to double how many moles I have. Now, if I don't change anything else, does that mean R is still the same? No. But can that happen? No. R has to stay at 1. So if I double this, something else has to change. Now, for our case, we're going to keep it simple, at least for now. Let's say the pressure is the only thing that changed. Well, what number can we put there to keep this at 1? We could put a 2, right? 2 divided by 2 cancels to 1, right? And now we still have 1. But notice, if I change this, that has to change. Okay? Well, what if the pressure, let's say we're dealing with a metal tank. Can the, or we're dealing with the balloon. Is the pressure, let's see. No, yeah, that one, the previous one was if we're in a balloon or something like that. Well, what if the pressure cannot change? What if it changes, if the pressure tries to change, something else happens? So it might be the volume that changes. 2 divided by 2 cancels and we got 1. Okay? What if the top cannot change? What if the temperature is the only thing that can change? Well, I could put a half down here, right? Because that's still 2. 2 times a half is still 1, right? 1 times 1 divided by 1 is equal to 1. Okay? Now, what happens in reality in many situations? If I change this one, well, this one might change to 0.5. This one might change to 4, and that one might stay the same. And if you do all the math, what you'll see is 2 times a half is equal to 1 over 1, which is still 1. So I change this and I change everything. Okay? So we have to be very careful with how this works. So how can we simplify this? Okay? Here's how we can simplify it. We could take this equation and we could say our first condition, our starting condition, is equal to R, which has to be equal to our second condition. And by logic, if this is true and this is true, then I can get rid of this, and that has to be true. And that's what we're going to be dealing with as we go forward from here. So now let's work a couple practice problems.